Okay, today we're going to talk about compositions of transformations as we continue to work through translations, reflections, rotations. And today we're going to combine those all into one step and take a look at what happens when we take two transformations in one step. And that will lead us into talking about tessellations, a kind of an art style that the artist M.C. Escher made famous. And here's one of his artworks. It's where you combine different shapes so that there's no overlap within the figure. So we'll learn that today. First thing we'll take a look at is what's known as a glide reflection. A glide reflection combines two transformations, the translation or the glide, and then the reflection. So you can see the original image and then where it maps onto after the slide or the glide and then the reflection. So we'll do that in our first example here as we take a look at the triangle ABC with coordinates 3, 2, 6, 3, and 7, 1. I have them listed on the table here and graphed. We want to find the image after the glide reflection. So first we're going to translate in the glide reflection and then we'll reflect. So why don't you take the time to find the new coordinates after the translation and then the reflection. So pause the video. Here's going to be our translation and here's after the reflection. And see what the new coordinates will be. Okay, so notice after we perform the translation, let me get my pen here. After we perform the translation, the new coordinates are listed down below. You can compare with what you had. And then after we perform that translation, notice the coordinates as they move, it gets translated left, as we can see in the arrow notation, goes left 12. The y coordinates stay the same, so it just translates to the left, and then it reflects across the x-axis. So notice just the y coordinates change there. And we can see as we go towards the translation and then the reflection, we get our new coordinates as we complete that move, the glide reflection. Next, let's take a look at another type of composition of transformations. Here we've got the segment RS. I have it graphed over here and its coordinates listed. We want to reflect it first and then rotate it 90 degrees about the origin. So why don't you take the time to practice getting the new coordinates for the reflection, and then for the second transformation, let's do the rotation, and we can do that one over here. So pause the video and restart it when you're ready to check to see what you got. Okay, so notice as we perform the reflection across the y-axis, just flips across the y-axis. We get our new coordinates there. And then once we rotate that figure 90 degrees, we rotate that image 90 degrees, and we get the new coordinates for R double prime and S double prime. Notice, I know I didn't draw the lines very straight, but they maintain same shape and size. So throughout this whole thing, these are congruence transformations, no matter how many times we do that. Let's now explore double reflections. So we've taken a look at translation and a reflection and a rotation and a reflection. Let's look at some of the properties that happen when we get a double reflection. So we'll take a look at that on GeoGebra. So first of all, let's take a look at what happens when we have parallel lines that we're reflecting across. So here we have triangle ABC reflecting across the line x equals -1. And then we're reflecting that again across the line x equals 4. Notice these lines are parallel. And let's just take a look at some of the properties that exist. Notice if I move this one, see the effect that it has on both the other images. So just take a second and figure out what you notice or what you wonder about with those double reflections. Jot down anything in your notes and then we'll discuss some of the properties that result through this double reflection. You can even click on the link and try this on your own. Okay, so hopefully you noticed some different things about this double reflection. The first thing you may have noticed is that as I go from triangle ABC to triangle A double prime, B double prime, C double prime, is maybe you notice that that looks like, well, if I would have just translated it, the double reflection takes me back to a translation. Another thing that maybe you noticed was that these points, if I connect A prime, and A double prime on B through its images, then we see that those lines are perpendicular to the reflection lines, because we know that lines of reflection will be perpendicular to what they're reflecting across. We know that we see that it applies to both lines as well. The other thing that maybe you noticed was maybe you looked at the distances. So let's just take C for example. So C to its image, C double prime, as we count along the number line, is a length of 10 units. As we take a look at B to B double prime, that's a length of from -5 to 5, 10 units as well. And A to A double prime, same thing, is a length of 10 units. What connection is that 10 units there to our lines of reflection? Well, if I go from one line of reflection to the other, -1 to 4, that's a length of 5 units. So let's drag those points around and compare. No matter what happens, B to B double prime is still a length of 10 units away. No matter how close I move that, if I move it right on the line of reflection, we are still 10 units, no matter where we go. And hopefully you can see why it is 10 units. It's doubled this length of across from these lines of reflection. Because if we take a look at, well, C is being reflected. If it's a true reflection, it's the same distance from the line of reflection. So this is 1 unit, and this is 1 unit. And now it's being reflected across the next line, so that is 1, 2, 3, 4 units away. So that will also reflect across 4 units away. So this total in here gets reflected out both ways. That proves why that this length between the lines of reflection will be double as we compare these other 2 points. So if we say D is the distance, and we can record that in our notes here. Let's get back to the slideshow. There we go. So the reflections and parallel lines theorem. The two things that we talked about, the line is perpendicular to our line of reflection, and D is the distance between our 2 lines of reflection. So from the image, or from the original to the image, is going to be doubled in length. So you can take time and read through those, pause it if you need to. So let's apply that theorem. In the diagram, a reflection line K maps, sorry, I can't talk very well, segment GH to G prime H prime. And then a reflection line M maps G prime H prime to G double prime H double prime. We also know that HB is 9 and DH double prime is 4. So we know these lengths as well. So take the time to go through, try these 3 examples on your own and compare with what we get on the video. So pause it and try it on your own. Okay, so the first thing we looked at, well, segments congruent to HG. Well, I know in reflections these will all be congruent. HB, well, I know this one and this one are the same since they are reflections. And these, well, these aren't equal to HB necessarily, but GA will be congruent with GA here. And those are the ones we know for certain. Does AC equal BD? Well, AC and BD. Yes, they should be congruent because as we take a look at that, well, both of these sides are perpendicular to the lines of reflection. Therefore, we've got 90-degree angles here, which means we've got a rectangle. And so these opposite sides are congruent, and so would AB and DC. Now as we try to find the length of G to G double prime, so that would be this length here. Well, we know that it is 9 from B to H, and we know that it would be another 9 here. D to H double prime is 4, reflect across is 4. So we know that this total length, 18 plus 8 is 26 units. We know that any other reflection of any other points will have to be 26. So from G to G double prime would also have to be 26 units as well, because it's going to be double the distance between these two lines of reflection, which we said was 13. All right, now let's take a look at reflections and intersecting lines. So we can do that by looking at GeoGebra again. And we'll look at a different app this time. It will help us explore that. So now we're taking a look at another double reflection. This time we have intersecting lines. Before we had parallel lines. So we have triangle ABC being reflected across this line here. Let's call it K. And we see its reflection maps with A prime, B prime, and C prime. And then that's reflected across line M to get A double prime, B double prime, and C double prime. So what do you notice first of all? What connections do you see with previous transformations? Well, if we compare this with its image, it appears that perhaps it's a rotation. If we compare the points, it looks like we're rotating all the points clockwise. So as we compare those, we see that there might be a connection with rotations. So let's just take a look at the angles between the lines. So we have a 60-degree angle here, which would mean this one is 120 and 120 here. Since these are supplementary and vertical angles, this would have to be 60 as well. The angle of rotation between these objects, we can calculate that on GeoGebra. We see as 120 degrees from A to A double prime, and that would be the same for any of the other points, B to B double prime. So the connection there, and let's see if we can move these points at all. Move that line so that they intersect at different place. So now this becomes a 76-degree angle, and notice if it reflects across, notice reflect, reflect, it ends up with double the angle. So anytime we have intersecting lines, as you can see, when we reflect it across, this angle between the two intersecting lines, we could have just rotated double that degree mark. So it's kind of cool when you can play around with it and see that it holds true for all circumstances. And you can see the connection there. So we can put that in our notes now. There we are. So reflections and intersecting lines theorem. Just what we talked about, this angle between the two intersecting lines will end up being half of what the angle would be if we rotated the figure instead of reflecting it twice. So we can take a look at an example here. We're reflecting across line K, then a line along line M, 7 degrees between the two of them, which would mean as we're taking a look at those, we would see that that would be rotating 140 degrees. Okay, finally let's talk about tessellations. Tessellation, as I mentioned at the beginning, is a collection of figures that cover a plane with no gaps or overlaps. We use transformations to make these. So you can see that we could rotate this to get to the lighter one, rotate it back. We could keep rotating, or once we get these, we could just translate them over. Same here, translate. Here, this is a rotation. So multiple transformations that are applied in here. A regular tessellation is one that involves congruent regular polygons. So this would be a regular tessellation because we have equilateral triangles being used. This would not be a regular tessellation, but we'll talk about that type of tessellation. First of all, I'll give you a link that you can play around with these, but you want to determine if these shapes tessellate. Do they fit together with no gaps or overlaps? So if you'd like to try this out, you want to see if an octagon, trapezoid, or regular hexagon tessellate. If we click this link, it'll take us to this tessellation creator, and we can try that out. So the first one we had was an octagon. So as we take a look at that, pull out my octagon and just try to plot those on and see if we can fit those in there. And as we try it, we'll see that no matter what we do, there's going to be this gap in here. So we would say the octagon does not tessellate. So you can try the other shapes. I know we don't have a trapezoid on here, but you can try any of these and see if they tessellate, and see if you can figure out why something would tessellate. All right, so the octagon we discovered does not tessellate. Trapezoid, we can tessellate that one. And the regular hexagon, we can tessellate as well. Here's an example of that trapezoid tessellating. We can just rotate the figures around and make them fit. And the hexagon we've got here, right here. So we can match those up so that there's no overlap. We see that there's 120 degrees in this hexagon angle. 120 is 240 plus another 120 is a total of 360. You see in a tessellation we got to have 360 degrees. If there's any more, any less, there would be overlap or a gap. So the other thing with tessellations, we can do a tessellation with kind of irregular shapes. This was a regular hexagon, so it was a regular tessellation. But if we have shapes that are kind of odd, start with a triangle that we know tessellates. If we cut a piece out from it and move it to the other side, you can see that those match up as we rotate those figures around. If you want to play around with that a little bit, you could take this website and we just change the figure a little bit, and since it takes it from this part, it adds it over to this part so that when we rotate the figures they all match up, and it gets kind of a cool looking piece of artwork. So that's what MC Escher based his work on. He started with a basic shape, whether it's a triangle, rectangle, or hexagon, because those add up to 360 degrees at each corner, and just took that basic shape and just adjusted it as he was working through it, and found a way to make it look pretty cool. So, if we use two shapes, same thing. I could use, put those together to form a tessellation. It doesn't have to just be one shape. So I could take the octagons that didn't fit before, but notice that there was a gap in between those octagons. And if I put a square in between and rotate it over, rotate my square, and if I move that back in, not quite there, it should fit in there. I have to work on that a little bit, but you could play around with that and find out which different shapes would fit together. So then I just keep putting the different pieces in there and make sure there's no gaps or overlaps, and if I can do that, I've got myself a tessellation. Notice if I wanted, I could put equilateral triangle, but notice that doesn't fit because there's not enough degrees to match up in there. So we would see that it does work with the square and the octagon. All right, so we've learned a lot today about glide reflections and different compositions of transformations and the properties involved, and that led us to work with some artwork or art forms known as tessellations. So if you want, go ahead and enjoy and play around with those tessellations, and we'll see you next time.